Good morning or good afternoon, everyone. Welcome to today's webinar comparing RapidIO and SAE 6802 or TTEthernet using dynamic timing and power simulation. My name is Ranjit and I am your host for today's webinar. The webinar is going to be approximately about 45 minutes and then we will be having a question answer sessions. Okay. Before we get started, I would like to go over a few items so you know how to participate in this event. So we have taken a snapshot of an sample attendee interface, and you should see something like this on your screen right-hand side. If you have any questions, type in your questions in the chat window, and we have engineers in standby, and they will be answering all your questions. And also, I'll be answering most of the questions during Q&A session as well. So please feel free to post in your questions during this event, and that will actually help us to kind of answer all your questions during the session itself. For those of you just joining us, welcome to this webinar on comparing RapidIO and TTEthernet or SAE 6802 using dynamic timing and power simulation. So purpose of this today's webinar is to highlight the significance of these two technologies and try to identify the criteria to make decisions on selecting next generation interconnect for your avionics or HPC platforms, or for automotive platforms, or even for data center applications itself. So I'll be going over a few demo examples to highlight or to show you how modeling and simulation can help you in making architectural decisions on selecting one of these two interconnect technologies itself, and also how you can utilize the kind of options these two technologies provides as well. Okay. So if we get started with TTEthernet itself. So TTEthernet is a scalable open real-time Ethernet platform used predominantly for safety-related applications. One of the main reasons for selecting TTEthernet is as it offers deterministic real-time communication and also ability to transmit best effort and rate-constrained traffic along with timing-triggered traffic in the same network itself. And also it requires low hardware cost, and also it is well established with open world standard itself. And also it is a highly scalable technology as well. But if you look at the RapidIO, so RapidIO offers reliability and also cost effectiveness, and also it provides you extremely high bandwidth in the range of 1 gigabits per second to 160 gigabits per second. And initially RapidIO was considered as a kind of successor to the processor interconnect technology. But now we can see that the presence of RapidIO technology is in wide range of applications, all the way from computing, defense, networking, avionics, and even the kind of 5G base stations of the communication technologies as well. And also it is predominantly used as a kind of chip-to-chip or board-to-board and chassis-to-chassis interconnect technology as well. In which you need a kind of a determinism as well as kind of very high bandwidth requirements as well. Okay, so if you look at the kind of application areas where TTEthernet and RapidIO are kind of used in the common areas, or we can look it into as avionics or spacecraft or in defense or in industrial applications itself. If you look at the avionics itself, so RapidIO has been used and used as a kind of backbone technology predominantly for your next generation integrated modular avionics architectures. And also we are seeing RapidIO as a kind of deterministic high-performance interconnect in spacecrafts as well. And also both the technologies are predominantly used in the areas of hard real-time embedded systems as well. So this actually takes us to a kind of conclusion saying that these two technologies may be competing each other, but the reality may be different, and the requirements could be different as well. For example, if the system requires a high bandwidth, and if the system can compromise with regards to the determinism, then RapidIO would be a kind of great fit. But if the determinism is a kind of highly crucial for your requirements, and you can compromise in terms of bandwidth, then a TTEthernet could be the right fit. But is that the kind of criteria that you would look for, or you should be looking for? Definitely not. So let us look at the kind of criteria that makes us, or that helps us to select the right technology as an interconnect for your upcoming technologies in terms of interconnect, things like that. So if you look at that, the kind of criteria we can list out as a kind of high bandwidth and low latency, or low system power with high performance, and a safety critical but still fail operational, and a deterministic and timing critical requirements. And also if the system is a kind of peer-to-peer multi-processor network that you would be interested in exploring or developing. It could be the kind of network time and space partitioning requirements that you might be having. If you look at these kind of questions, or if you look at these list of items as a kind of criteria to select a standard, this actually tells us in a first shot by looking at the specification of these two standards itself. So if you look at the high bandwidth and low latency, definitely RapidIO is a kind of just right fit. And also if you look at the low system power with high performance, again RapidIO helps us in meeting these requirements. And if the requirement is in terms of safety critical and fail operational, mostly in the area of avionics control, so TTEthernet plays a huge role in this space. And similarly for deterministic and timing critical, again TTEthernet proves that this is the right contender. And if you look at the peer-to-peer and multi-processor network, RapidIO is the right fit. And these are the kind of items that we could capture by looking at the specifications of these technologies. And in most of the cases, the scenario may be quite different. You may need to have a safety critical fail operational requirements, along with you may have peer-to-peer multi-processor network. So you need to have a processor board that works even if something goes wrong in the network. You may have to have triple mode redundancy or dual redundancy networks, things like that. So in that case, the question may be, should you go with RapidIO, or you should go with TTEthernet, or you should use both the technologies and try to achieve the requirements. And these are the kind of criteria are almost difficult to just looking at the specification, and it requires a kind of careful evaluation, and also it requires a kind of proof of concept for making sure that the system that what you have meets your or provides you high bandwidth with low latency. And these requirements or the criteria may not just depend on the kind of interconnect technology that you are using, but it may also depend on the subsystem that you are using around it. So you will have to kind of construct a complete system platform and try to explore the system performance or system behavior with various workloads, and try to say if you are still able to meet your requirements with a particular technology, or you should be going to a different technology. So to achieve these credentials, or to achieve these characteristics, system level modeling in simulation plays a huge role, because it actually helps you to model your complete system architecture, including both hardware and software. And also it enables you to kind of conduct varieties of explorations by changing your configurations, by changing the topology itself, or changing the subsystems, how you have connected, or it could be changing the way how a particular node is interacting with another node itself. And also this introduces a lot of challenges in terms of performance as well as power consumption. And also at the same time, you should be selecting the right interconnect itself. So that meets your safety requirements, and also that meets your performance requirements as well. So a system level modeling actually helps you to predict the performance and power consumption of your complete system platform by measuring the latency and throughput, or bandwidth and peak power consumption, or average power consumption of the platform, and how exactly the applications are executing on the target platform itself, and things like that. And also in addition to that, you may have to select the right system components as well. So you'll have to make sure that the components are running at the optimal clock frequency, and the cache or memory hierarchy is correct, or bus topology, how you have defined your algorithm for the bus select that you have selected. And these are the kind of problems that goes along with the selection of your interconnect as well. So you will have to consider not just your interconnect portion, but also the remaining subsystem around that interconnect as well, to make sure that the complete system works very well even after integration, or even after it goes off for the implementations, things like that. And also you should be able to identify the kind of bottlenecks or the problems early in the design phase, so that you can eliminate the problems that could come up maybe after implementation, or once the system is ready to deploy. Okay, and also one more problem that people are coming up with adopting to a new technology or things like that is communication between the teams itself. So a system level model can actually help in communicating between teams, so that it actually provides a clear idea or clear details about what exactly each subsystems are meant to be, and how they are interacting with the remaining portions of the systems itself. Okay, and these are the kind of details, if these details are available right up front, this makes the life of implementation engineers a whole lot easier. And also it helps the marketing teams and also vendors and customers to capture the requirements or the information early in the design phase itself. Okay, so one of the other characteristics or advantage of system level models is to be able to explore the system level model by changing the nodes, or adding an additional node, or removing a particular node from your system. For example, let us say you need to have an architecture with about 20 nodes, and you should be able to identify whether RapidIO, I mean, you should be going with RapidIO, or whether you should be going with TTEthernet or things like that, or maybe PCI Express or things like that. So a system level model can actually help you to dynamically add as many number of nodes to your RapidIO switch itself, and try to understand what happens if you add so many nodes to your switch, and what is the impact of that on the total system performance as well as power consumption of the complete system itself. And also it allows you to capture the system behavior with changes in traffic, or changes in the kind of, if you change the algorithm which you have used in the network itself, or if you change from star node to a kind of linear node topologies, things like that and all. Okay, so you can actually explore your system level model or your RapidIO based model or TTEthernet based model by using system level explorations to be able to identify the kind of problems that you could expect maybe during implementations and things like that. Okay, and typical analysis reports that you could expect out of a simulation model to be able to select a particular technology would be what is the latency that you're getting. So definitely your RapidIO should be actually returning your latency in terms of microseconds. And in time-triggered Ethernet, you will have to make sure that the packet of information is actually available in a particular time slot. And also you should make sure that the nodes that are connected to the network are completely synchronized. So you should be able to see these kind of behaviors and activities of your network or the system by conducting analysis itself. And also you can actually try to understand how different types of traffic classes actually helps in policing or shaping of the traffic itself. Okay, for example, if you consider TTEthernet itself, it supports time triggered or best effort traffic and rate constraint traffic. So what happens if a particular node can generate these three different types of traffics, and whether the node, which is actually on the other side of the network itself, can be able to receive the transactions maybe in best effort or rate constraint, or what is going to be the latency that you could achieve with a particular traffic class itself. Okay, so these kind of explorations you can conduct using these simulation models. And also one more interesting point over here is that you can integrate your performance analysis along with power analysis itself, which means you can actually conduct performance versus power trade-off studies to make sure that the system is actually meeting both of your performance as well as power requirements with the architecture that you have selected. Okay. And here's an actually example model of a RapidIO model, which is actually constructed in VisualSim. The model that you're looking at over here is actually the two switches are configured for IDT RapidIO switches. And in here, on the right-hand side that you can see here, is a instrumentation card. And also we have one more communication card in the right-hand side. And these two resources, or these two endpoints, are considered as a kind of traffic generators in this case. We have considered these two endpoints, or we have modeled these two endpoints at a very high abstraction level, but we can go to a very detailed abstraction of these models as well. In this case, these two resources can actually send read or write requests to the node, which is actually the DRAM on the other side of the IDT switch over here. And we are actually trying to capture what is going to be my write latency or read latency. And also at the same time, we are trying to capture what is going to be my instantaneous power consumption and also the average power consumption of this particular system model. Okay, and in this case, we are actually integrating both performance analysis as well as power analysis in the same model. And these power manager, which you are seeing at the top, actually allows us to kind of enter in details such as the power values of these two switches and the devices in different states of power. What is going to be the power consumption in active state or sleep state or standby state, things like that. And these libraries are completely configurable. And I'm going to show you the parameters in a little bit, which means you can actually configure the RapidIO switch that meets your specification or the requirement itself. This particular RapidIO switch can be from a different vendor, and you can actually configure this particular switch to meet that particular vendor specification itself. And that actually allows you to kind of explore the system performance with the current technology as well as the future technology, which means the RapidIO can be the IDT switch in this case could be supporting my second generation RapidIO, and in maybe after 2 years or 3 years down the line I may have fourth generation of RapidIO technology. So if you have sufficient information about what is going to be the changes that you could expect in fourth generation or fifth generation, you can actually enter in those details as a set of parameters and try to understand if the system supports your fifth generation of RapidIO technology itself. So that actually makes it possible to kind of model your custom switches, RapidIO switches, as well as the standard RapidIO switches as well. Okay, and here's the sample analysis that we have conducted, and the model that we have constructed is actually having 3 endpoints, which I just showed you, with instrumentation and communication control and a memory. And these instrumentation and communication control devices actually provides read requests and write requests. And the size of the data that it sends could be all the way from, all the way up to 256 megabytes. And the RapidIO switch that we have over here is IDT specific RapidIO switch, which is having a buffer size of about 30, and it runs at 1 gigahertz of clock. And then the memory itself is actually a DDR2 memory, which is running at 1 gigahertz. And the kind of explorations we are actually trying to look at is to try to understand what happens if I have a read request and if I have disabled my flow control in my RapidIO switch itself, and if I consider overhead cycles of 2. And if you look at the kind of reports that we have generated over here, in this case we have 3 reports. One is power consumption report, and the other is packet latency, and the third is the textual report is the detailed information or statistics of the RapidIO switch itself, and also other hardware architecture elements, which includes your memory and other IO devices, things like that. In this case, we are actually looking at what is the RapidIO throughput that I'm getting over here, and also we are looking at how many number of packets entered, how many exited, and what is the maximum occupancy in my buffer itself, things like that. Again, one more interesting point over here is that these are not just a kind of standard reports that it generates, and customer or the user can actually add customized reports for the model that they are generating, which means they can actually try to understand a particular, they can generate answer for a particular question itself and try to optimize the simulation model in a much quicker way as well. Okay, and in this case here, the power consumption plot that I have placed here is actually, the blue one is actually average power consumption, and the red one is blue one is instantaneous power consumption, and the red one is average power consumption, and x-axis is simulation time, which means how long you're running the model, and y-axis is power consumption in watts itself. And at the bottom we have the packet latency. In this case we just capture for read transactions or read requests, and here we are plotting the end-to-end latency for a read request itself. So how much time your network has taken to reach your DRAM and get the data back. If I do a kind of minor modification to that particular model and run simulation, I'm going to go to VisualSim tool now. So here we have the VisualSim environment, and the space that you're seeing over here is actually the workspace in which you will be constructing these simulation models. And in the left-hand side we have the list of library blocks. So that actually allows us to bring in or drag in these technology libraries and conduct explorations as quickly as possible. In this case, I can go ahead and bring in these RapidIO switches, and these switches are provided with a set of parameters. So in this case, this particular RapidIO switch parameters are configured only for the specifications available with IDT RapidIO switch, and these parameters can vary based on the type of, based on the vendor of that particular RapidIO itself. Okay. And in this case, what I have here is I have connected only one traffic over here, and when I hit the run button over here, and it actually provides me the list of simulation results, and in this case I'm actually capturing my write latency. And if I actually add the read activity as well to my simulation model, I just actually connected the other transaction source here, and when I hit the run button, now I have both read and write requests going across my network itself. Now I can actually see that as there are a lot of activities going across my network or RapidIO switch itself, now I can see a kind of increasing latency plot here, which means there are a lot of buffering activities going across in my channel itself. So you may have to increase your switch speed, or you may have to decrease the rate at which you are receiving the traffic, or you may have to change the flow control mechanism, how you have defined things like that. Okay, and these textual reports, actually in this case we are capturing details such as what is going to be my SDRAM throughput for the workload what I have given, and what is going to be my utilization of my components. And these are the kind of reports, a few set of reports that I'm showing you, but there are about 2,000 different types of reports that you can generate out of these simulation models as well. Okay, at this point I'm going to go back to the presentation. So here is actually an example of a large RapidIO based system model. Notice that in this case here we are not using any IDT specific RapidIO switches, but instead this particular RapidIO backbone is actually completely modeled using a custom RapidIO generator itself. So to generate a custom RapidIO switch itself, we actually provide two libraries specifically. One is RapidIO node, and then we will actually provide a serial switch. Both actually models particular RapidIO switch that you're looking for. Okay, and in this case we have actually integrated multiple processor models. In this case we have PowerPC processors, and we have Xeon processors, and also we have data coming in through PCI Express bus itself. And also we have additional read and write requests coming from custom interfaces, things like that. And this is a kind of example of showing you how big the system can be, and the kind of explorations that you could explore with VisualSim and RapidIO libraries itself. Okay, and here if you look at the TTEthernet model, TTEthernet, again, we provide a set of library blocks to quickly model your TTEthernet network itself, and it mainly includes nodes and bridges and traffic generators. And if you look at the block that I have highlighted over here, in this case actually what we have is we have three TTEthernet nodes, or I can say three endpoints, and out of three, two endpoints are connected to ECUs. In this case, they are coal-fired processor models, and it is a blown-up view of ECU1, which is actually a hierarchical block over here. In this case, what we have is a custom bus arbiter and a memory and an SRAM connected to the processor model and all that. And in this case, the block which is actually responsible for initiating the traffic is TTE node 1 and node 3 over here, these two. And TTE node 2 is actually a destination node point in this case. And the kind of traffic, as I mentioned earlier, this supports time triggered as well as best effort and rate constrained traffic generation. And how we do that is we actually have a table to generate different types of or different classes of traffic. And that particular table is actually helping this traffic generator to generate either time triggered or rate constrained or best effort traffic. In this case, what we have here is this identified TT1 actually tells me that I need to generate time triggered traffic, and the source is is node 1, which is actually this guy, and the destination is my node 5, which is actually the TTE node 2 block, which is actually connected to my ECU2, and I'll be sending at so much Mbps and what is going to be the data size. And these details are modeled as a list of parameters, okay? And here how we can define different types of traffic classes and enable kind of integrating those networks to the processor model and try to understand if the latency what you're getting out of the network or the throughput what you're getting out of the network is sufficient to meet your requirements or not. Okay, and the kind of analysis that we have conducted with a particular model is here again we have three TTEthernet nodes, core 5 processors at node 1 and node 3. And in this case, node 1 and node 2 are initiators and node 3 as a target. And bridge connects node 1, node 2 to the node 3 block. Okay, and you might have seen that there are no wired connection between node blocks to node bridge block, which is actually maintained by a named connection, which means you don't really need any wired connection going from one block to another. Okay, and the kind of explorations that we're conducting over here is each initiator actually generates a time triggered or a rate constrained or best effort traffic streams, and I can actually completely control these, and I can make sure that one particular node can only generate a rate constrained, or only one particular node can generate only time triggered traffic, things like that. Okay, and also we have considered other configurations, such as I need to consider all the nodes as synchronization masters and bridges as compression masters. Okay, and the TT traffic size that I've considered here is about 64 bytes and a shuffle percentage of about 100%. Okay, and when I run the particular model with these set of configurations, by default, we actually generate reports such as the latest latency graph, as well as textual report with throughput and latency information. And in this case, in the right-hand side, you can actually see a list of streams that we are plotting over here. I will go back to VisualSim right now, so you can actually see this particular analysis reports quite nicely. And I'm going to run this particular model. So model is running right now, and the details what you have here, N1 to N5 RC1, this actually tells me that node 1 to node 5, and the type of traffic that I'm sending across is a rate constrained traffic. And if I need to look at my time triggered Ethernet traffic latency, I have N1 to N5, which is actually a TT1. And that's actually quite high, somewhere near 2.6 milliseconds of latency that I'm getting. But apart from that, rate constrained and best effort latencies are somewhere near 0.5 to 0.6 or 0.06 latencies, things like that, kind of quite less latency. Okay, I'm going to stop this particular simulation. And what I can do is I can actually go ahead and change the type of traffic that I'm using. And to do that, we actually provide traffic generation tables, and which I just showed you. I can actually change these configurations and run the model to be able to model the kind of workloads that I have with my current requirements for a particular project. So these are the kind of generic tables that we provide to configure your time-triggered Ethernet network to model your current or future requirement-based system models itself. Okay, I'm going to go back to the presentation. And as I mentioned earlier, the libraries are provided as a configurable libraries which means you have full flexibility to change the configuration of both RapidIO and TTEthernet libraries to model it as a custom component or a standard component from a particular vendor or things like that. And we already provide many RapidIO switches from different vendors as well, and IDT is one of them. And these libraries are integrated with statistic generators and results generators, which means you don't have to kind of put your effort on customizing generation of traffic or generation of reports, things like that, which is already implemented. And these models are provided to conduct performance versus power trade-offs as well, which means all the libraries supports power analysis as well as performance analysis at the same time. So which means you don't have to construct two different models to understand what is going to be the power consumption of my RapidIO switch-based model versus power consumption as well as performance of my TTEthernet-based model. And these libraries are highly accurate as they are validated against the standard, and hence these libraries provide better performance as well as power values at system level models itself. For example, to give you an idea here, this is an IDT RapidIO switch, which is actually provided with a set of parameters, and user can change these particular parameters by double clicking on the block and changing these values and all that. And if you notice over here, this also can generate you the debug messages as well, which actually helps you to kind of understand how exactly the traffic inside your switch is going across from one endpoint to another endpoint in your RapidIO switch itself. So you can actually understand the internal behavior of your switch as well, and try to debug or try to perform or try to optimize your network in a better way as well. Okay. And to support that, here we have a list of other additional modeling libraries as well, which actually makes it possible to construct a complete simulation model of your complete system, including your processor models or networking and storage and SOCs and other library blocks are also available. And the library blocks that we provide for RapidIO and TTEthernet are compliant with all these other additional libraries that we provide as well. So it doesn't really require any kind of additional setup to be able to talk to between two different blocks, things like that. Okay. A little bit about VisualSim itself. It is a completely graphical and hierarchical modeling and simulation tool, which you just saw here, and it doesn't require any kind of coding effort to construct any simulation models, which means you graphically construct these models and conduct explorations. And the libraries are provided at different levels of abstraction. Based on the level of details that you have, you can select the level of abstraction and start building up the model. And the main purpose of constructing these simulation models is to conduct architecture exploration or performance analysis and hardware software partitioning and power analysis, things like that. And the library blocks are used to assemble your hardware, software, network, and traffic, and generate custom reports or use cases for the implementation teams, things like that. Okay, and why exactly performance analysis with VisualSim helps you? The answer is in multiple ways, I would say. Because if we actually look at any of those complex systems nowadays, most of the systems are actually having a characteristics such as limitations in terms of resources. You may have very less resources, but you have a lot of but you may have a lot of processing requirements that needs to be done on the platform itself. And VisualSim actually helps you to model your hardware and software in the same platform and enable you to looks like I lost my audio connection.
Muted. Unmuted.
Okay. In terms of the performance analysis, one of the advantages that you get by doing system level power performance analysis that you can look at the big picture, which is the whole system. So in this particular case, you can actually have a backbone switch with multiple RapidIO nodes. In this case, there's 4, but we've got customers that have put together 100, 125 nodes to elaborate the entire system. And then you can have interaction between them. For example, the processor on the top left could be accessing memory on the bottom right. The other advantage is that if you want to have any sort of scheduling or handling of resources across the entire switch network, you have the ability to do that as well, because what that allows you to do is allows you to look at, if there's any data dependent behaviors, or if the scheduling could increase your performance, this could provide you an opportunity to do that. Another way to look at it is that you might have applications that might not execute entirely on a single processing platform, but may go across multiple processing platforms. So this allows you as well to be able to interactively view what the end-to-end latency is when the single application spreads across multiple processing units that are across a RapidIO or even a time-triggered Ethernet network. Now we'll move over to the next slide. I think Ranjit's back online, so he'll take over.
Yeah, I'm sorry about that. I actually had a minor network issue. I'm back online. So the main purpose of conducting system level explorations with VisualSim is, as I mentioned earlier, you can integrate your power analysis to your performance analysis model itself. And also, in addition to that, what we bring in here is we actually enable you to kind of bring in the kind of power levels or power details that you might have done with spreadsheet based analysis, things like that, into a simulation environment itself. As you may be aware of it, most of the power analysis may be done with spreadsheet based analysis. And if you notice there, the spreadsheet-based power analysis values may actually go into a level of only average power consumption. And it doesn't really capture the dynamic behavior of your system, and also it doesn't provide you the details such as what happens if there is a sudden spike in the system power consumption itself. And that particular spike may cause a huge performance variation as well as behavioral changes in terms of the system as well. And in this case, what you are seeing over here is the left-hand side, we have the spreadsheet which is having power information of different components. And also at the bottom, we have computed the average power consumption. And when we actually simulated with VisualSim, we actually have got this average power initially, but as we ran the model for a longer duration, we actually saw that after a certain time period, the power consumption of the system started going up. So this could be a kind of problem with a particular component that you have in your hardware architecture. So that may be actually consuming a lot of power, and even if it is not receiving any transaction, it may be always in on state. And these kind of problems can be identified with dynamic power analysis by bringing in spreadsheet data as well, and also by understanding or by looking at the state of different components during simulation run itself. Okay. And one of the other advantage with VisualSim that a customer can actually achieve is with VisualSim Architect, you will actually construct these simulation models and conduct varieties of explorations, things like that. And if you want to share this particular information or simulation details or the kind of reports that you received or the kind of values that you have generated to be able to make decisions on hardware architecture selection or topology selections or workload details, things like that, you will have to share it across the implementation teams, or you may have to share it with the suppliers or clients, things like that. So we actually have a tool called VisualSim Explorer that actually allows you to upload your simulation models to your private cloud itself, and you can share those HTML page which actually has the simulation model with a detailed information about the model, and the user on the other side, they can just click on the link in the HTML page and start running the model right from the web browser without a need for any software installation or any training, things like that. That actually helps in bridging the gap between post and pre-development challenges as well. And also it helps you to gather information from the client or from the suppliers, things like that as well. Okay. So to conclude this particular webinar session, so the main purpose of conducting system level explorations to identify a particular network interconnect or a technology is to be able to make sure that the performance and power requirements are met, and also you need to make sure that the safety requirements or determinism is kept alive in your system model itself. And by looking at these different characteristics or the kind of criteria that I have showed earlier, to prove those criteria are met for the selected architecture, for the selected interconnect, you need to actually have a simulation model that actually shows you a series of different workloads and the kind of configurations that you have worked with and all that. Okay, and these actually are earlier design explorations actually helps you to gain more confidence on the selected architecture, and also try to capture the bottlenecks that you could expect later in the design process as well. Okay, and also these simulation models, once you have constructed, maybe if it is a custom or a standard technology-based architecture, you can share it with your design team or the implementation team or with the clients. They can actually provide the feedbacks early in the design phase, and you can actually make those changes as requested by the people on the other side as well. Okay, so this concludes this particular webinar, and the session is open for question and answers, and I've seen that most of the questions are actually already answered by our engineers, and if you have any questions, please post in your questions in the chat window, and we will be sending you a link to download this particular presentation as an email within 24 hours.